So the argument is this portion here. We start out with making a couple of of statements, and these are like our P. So the piece that we use here, Pi, is basically, that's a hypothesis, and then they're all using the logical AND, so we always have the conjunction. And then we have Q, which is our conclusion. So I don't know, that handwriting doesn't look that great. So all our basically all our arguments have this format. And once we take them into, once we convert them into the formal logic, we can use the rules, the equivalence rules and inference rules, to convert it into, basically convert the expressions, so at the end that we have an expression that is a, basically it comes down that to prove, what we need to prove is that the whole expression is always true. That it's a tautology. So this is basically the process of, in the exercise of all of this here. So this is basically the process. If we start out with a format, let's say, for example, like this here. So we have a couple of hypotheses, and say this implies R, and that implies Q. Then we can convert this. Basically, what we have here is sort of an expression. If A implies B and B implies C, then A implies C. So these kind of expressions, can we show that? And that's basically what these exercises are about. If our first hypothesis is A implies B, and our second hypothesis is B implies C, and the third hypothesis is A. So basically what we do is, in order to prove this, we have three hypotheses. A implies B, B implies C, and A. So this could be, example could be, trying to think of an example. Give me an example. So if you say something, a verbal argument, A implies B. Say again? Can't hear you. All birds. Yeah. So this actually, let's take the. So basically, it would be like something like if something, then something. So let's say if, no. Oh, I might use different tools here. If bird flies, then can get the food. Oh, that's not good. So that's not a good tool here. So if a bird flies, let's call this F, implies, let's say implies E, that the bird can eat the food. If a bird eats food, then the bird gets bigger. Right? So these are basically, each of these sentences would be a hypothesis. We would say, okay, that's true. Yeah, we buy into that. Now we get a third piece of information that says, oh, look, the bird flies. So, okay, if the bird flies, we know the bird flies, and we know that if it flies, then it can eat. That means, well, now we basically proved that it can eat. So once we proved that here, so this was not given, that the fact that the bird eats is not given directly, it's indirectly given by the bird flies, and if the bird flies, it can eat. And then we basically continue. Okay, now we have E, and we can use the same thing. If the bird eats, then it gets bigger, and we know it eats because we just derived that. That means at the end we can say the bird must get bigger. So, and this is basically written in this format here. Our first hypothesis, A implies B, B implies C, and A. These are our three hypotheses, and all of them are basically connected with a logical AND. And then from that, basically, we can derive that the bird, I have a poor choice of letters here, but this was actually our E. We can, from the first hypothesis and the third one, basically saying if it flies, then it eats, and the last one, it flies, we can get E, and then using that, we can get the last conclusion here. And the inference rule that we used here is the inference called is rule MP modus ponens. So, there's basically a list of inference rules, and they have names, Latin-sounding names. Somebody came up with that, and then this textbook here uses a short version, so it makes it easier to track down exactly which steps have been taken. So what the exercise is now is that we introduced something else, and we introduced a new inference rule. So now we can say, because we proved it, that if we have something like A implies B, B implies C, and A is given, basically that implies, so if we have A implies B and B implies C, that implies that A implies C. So we can come up now saying if a bird flies, then it gets bigger. That's basically, we proved that sort of rule just based on on this chain of arguments, if you will. So pretty much everything follows the same pattern. And so here are the inference rules, and these inference rules are now for the propositional. For the propositional calculus, so without variables. But then they also work for the predicate formalism, for the predicate logic, pretty much in the same way. The only difference is that we now might have to have quantifiers in there, which introduces another set of predicates. So all these rules here that we see here, all these rules can be basically, you can prove that they're true, And so basically, often this is also if we have like our hypothesis, we might write them like this. So let's say we have two hypotheses. Basically what we say is P1, P2, and then we have some type, but what it says here derives, which is basically this one here. So whatever it would derive, this can be written as P1, P2 implies Q. And if you can show that this is true for every value of P and Q, or if you have variables with quantifiers and predicates, then with the given quantifiers is always true, then you have a new inference rule. So any of these, for example, could be shown, like this the proposition, it could be shown with truth tables or with the equivalence and inference relations. So sometimes the truth table might get too complex. So truth tables is like for having exhaustively showing all possible combinations. That's sort of a safe thing, but it can go very big. So we use equivalence and inference rules to take an expression and derive a new expression from that, which is somewhat a little bit of a puzzle, because what you need to find out is like which pieces you can, like which rule you can apply to get to the next step. And I trust you've done things like, solving a